Hi there and welcome back to Control Geek. In this video, I will explain a very important step that we need to perform on our control system before utilizing with any robust analysis. Before proceeding with the video, I need to state that the material along with the example are taken from the book Multivariable Feedback Control, Analysis and Design by Sigurd Skogstad. Before employing any concept in robust control theory, the undertaken system needs to be scaled. Scaling is very important in practical applications, as it makes model analysis and controller design much simpler. The scaling step requires the engineer to make a judgment at the start of the design process about the required performance of the system. To do this, decisions are made on the expected magnitudes of disturbances and reference changes, on the allowed magnitude of each input signal, and on the allowed deviation of each output. Let the unscaled linear model of the process in deviation variables be given as g hat, while the disturbance model is given as g sub d hat. The unscaled control signal u hat is subjected to g hat, whereas the unscaled disturbance d hat is subjected to g sub d hat. The produced two signals are added up to form the system unscaled output y hat. If this output is subtracted from an unscaled reference r hat, then unscaled control error is resulted. These processes can be realized in equation forms as given by y hat and e hat. A useful approach for scaling is to make the variables less than 1 in magnitude. This is done by dividing each variable by its maximum expected or allowed change. Let us deal with each set at time. For disturbances and manipulated inputs, we can scale them by dividing them by their corresponding largest values as shown. Here, d max hat is the largest expected change in disturbance, whereas u max hat is the largest allowed input change. Please concentrate on the word change in these two forms. The word change means the maximum deviation from a nominal value that should be chosen by thinking of the maximum value one can expect or allow as a function of time. For the variables y hat, e hat, as well as r hat, we can take the advantage from the fact that these variables are in the same units, so the same scaling factor should be applied to each. In this regard, two alternatives are possible. We either can use the largest allowed control error, or R max, which is the largest expected change in reference value for scaling. However, as a major objective of control is to minimize the control error e hat, we here usually choose to scale with respect to the maximum control error. Thus, we can scale the variables y hat, e hat, as well as r hat as shown. To formalize the scaling procedure, we need to introduce the following scaling factors. D sub e is the e max hat, d sub u is the u max hat, d sub d is the d max hat, and finally, d sub r is the r max hat. Before proceeding further, let us see what happens if we are dealing with multi-input, multi-output systems. In such case, each variable in the vectors u hat, d hat, e hat, and r hat may have a different maximum value. This will push the quantities d sub e through d sub r to become diagonal scaling matrices. This ensures, for example, that all errors are of about equal importance in terms of their magnitude. Going back to our original scaling problem with the introduced scaled variables d through r, and with the help of the quantities of d sub e through d sub r, these variables can be reformulated as shown. Let us concentrate on this new formula for the scaled variables and figure out how they change the original model of the process. By introducing this formula into the original unscaled model, the scaled model will have the following form. With both unscaled and scaled model, we can formulate the scaled transfer functions for the process as well as the disturbance model as shown. This then yields the following model in terms of scaled variables. In this new scaled representation, both variables u and d have a magnitude less than or equal to 1. And in order for the scaled error signal to have same property, the reference signal r need a bit more work. It is useful to introduce a scaled reference r tilde which is less than 1 in magnitude. This is done by dividing the unscaled reference, or hat, by the maximum expected reference change as shown. And according to our introduced notations, this also can be written as. Therefore, we can write the scaled reference R as R uppercase multiplied by the R tilde, where simply the uppercase R is given as. Here the uppercase R is the largest expected change in reference relative to the allowed control error. We can add this definition to our list on the right. The block diagram for the system in scaled variables is shown by the following figure. Keep in mind that now we have the magnitudes of the control signal U of t, the disturbance d of t, and the reference signal R tilde are less than or equal to 1. In addition, we can also state the control objective, which is to manipulate the control signal with its magnitude bounded, such that the control error is less than or equal to 1, at least most of the time. One last notation with this scaling procedure. Now, the worst case happens when the variable or the signal is equal to 1 in magnitude. Before jumping into an example, it is worth stating that when the expected or allowed variation of a variable about 0 or its nominal value is not symmetric, then the largest variation should be used for Dmax hat and the smallest variation for Umax hat and Emax hat. For example, if the bound on the disturbance is given as shown, and if the bound on the manipulated input is given as shown, then we can take the Dmax hat as 10 and take the Umax hat as 5. Do the same for Emax hat as with Umax hat. Let us demonstrate the introduced concepts through an example. The physical model of a room heating process can be simplified as following. We have a room that we need to keep the inside temperature T uppercase constant as possible. This temperature is measured in Kelvin. The room has a heat capacity of C sub V, which has the unit of joule per Kelvin. The wall of this room has a conductivity of alpha. The outside temperature is denoted as T sub 0. To control the temperature inside the room, we add a heater that can provide a heat source denoted as Q. It is desired that the temperature inside the room to vary with plus and minus 1 Kelvin. To drive a mathematical model for this room, we need to apply energy balance for the room. This requires that the change in energy in the room must equal the net inflow of energy to the room per unit of time. This yields the following first-order model. In this model, the last term, which is alpha by the temperature difference, represents the net heat loss due to exchange of air and heat conduction through the walls. For operation point, we can consider a case where the input heat from the heating unit has a nominal value of 2000 Watt, while the difference between indoor and outdoor temperatures is 20 Kelvin. These two nominal values result in a steady-state value of alpha to be 100 Watt per Kelvin. We can also assume that the room has a constant heat capacity value of 100 kJ per Kelvin. The next step is to write the model in deviation variables. If we assume alpha is constant, then our above model is linear. By introducing the following deviation variables, the driven model of the room can be written as. Let us put this equation along with the deviation variables aside and attempt to taking Laplace transform. By assuming 0 initial conditions and performing Laplace transform on the room differential equation, we can write the deviation in the room temperature as a Laplace function of both the control input and the disturbance as shown. Here, tau is just the ratio between CV and alpha. The last step is to scale this function. From our previous discussion, we can write down the scaled variables with respect to their corresponding maximum large changes as following. Starting with first variable, which is the process output Y. This variable is the room temperature. From our definition of the deviation from nominal value, as well as the assumed change in the room temperature, we can write the followings. The deviation is, whereas the nominal value is. Thus, the maximum change around the nominal value is 1. Therefore, we can say that delta Tmax is 1 Kelvin. This is same for the delta error max as well. for the control variable where it is the input heat from the heating unit. Let us assume that this heating unit can be varying from 0 to 6000 watt. With this variation and the deviation of Q from the nominal value along with the nominal value of Q, which is 2000 watt, we find that delta Q max is 2000. Please pause the video here and go back to part where I explained how to deal with unsymmetrical constraints on the control action to understand the delta Q max. Lastly, for scaling the disturbance with variation in the outside temperature of plus and minus 10 Kelvin, we can follow the procedure with delta T max and write down the delta T sub 0 max to be 10 Kelvin. Now we have found the scaling factors, we need to apply them to the system model and find the corresponding transfer functions. If you notice the driven differential equation for the room model, we have two inputs which are the control action delta Q along with the disturbance delta T sub 0. Thus, we need to write two transfer functions, one for each input. The first transfer function is between the output delta T and the control input delta Q. From the above differential equation and by letting the disturbance input to be 0, we can have the following transfer function. And by applying our scaling factors, the scaled transfer function would be as shown. And in numerical values, the final result is. The second transfer function is between the room temperature and the outside temperature. You can apply the same method that we have applied for the first transfer function to find that this transfer function is given as. Let us spend some seconds discussing these two transfer functions from control perspective. Note that the static gain for the input is 20, whereas the static gain for the disturbance is 10. The fact that KD is greater than 1 means that we need some control, feedback or feedforward to keep the output within its allowed bound, i.e. keeping the magnitude of the error less than 1, when there is a disturbance of magnitude 1. The fact that K is greater than KD means that we have enough power in the inputs to reject the disturbance at steady state. That is, we can, using an input of feasible magnitude, have perfect disturbance rejection, i.e. 0 steady state error for the maximum disturbance D equal to 1. To have more detail about such analyzation, you need to have information about something known as input-output controllability of processes in the control theory. With this had been said, we come to the end of the video. I hope you have gained a new information after this video. As usual, please subscribe to channel and do not leave the video without a like or a comment. See you soon, hopefully.